First of all, thanks to James for inviting me here. I thought that my initial fear was that I would speak in some different language. Well, I don't know English. But it appears that there are so many connections with what you do and work with the trenches. Not only David Bateman, who was one of the authors of the previous talk, is the PI of the project that I'm going to present, but also what Linda was talking about the survey of the needs and the need for a one-stop water data shopping is very consistent with what we're trying to do. What Don has presented about the problems with integrating metadata is something that we're trying to address. Thanks to Ken, I will try to skip a few slides and maybe make it faster. But before I get into the water stuff, Supercomputer Center is where I work for. I've been working there for 10 years. And it's one of a few large supercomputer centers that this program has started 25 years ago. So a few weeks ago, we celebrated 25 years. We have about 400 employees. Mostly the center is focused on data, not really compute science. We have supercomputers, of course, that can crunch a lot of data quickly, but mostly it's managing data lifecycle from publication to up-to-date preservation and archives. When I started at SDSC, I was working, my first project was working with National Archives, preservation of spatial data. Some of these projects are in earth sciences, neuroscience, astronomy, and one of them is in hydrology. This is my group that deals with spatial information systems, and we mostly work with earth science projects. They deal with geology, hydrology, ocean, so critical zone observatory, but also neuroscience, because you also have a similar issue. You have maps of the brain, and the problem is how you describe metadata about these maps and how you put this together. You already saw this. CUAHSI is the term that I had 4 years tried to remember. It stands for Consortium of Universities for the Advancement of Hydrologic Sciences. About 125 universities across the country, and it has 4 flagship projects: Hydrologic Information Systems, Measurement Facility, Synthesis, and Education Intelligence. I'm going to talk about the first one. Data Green is a PI. It's a group of universities that includes University of Texas at Austin, Utah State, Idaho, University of Carolina, and us. And this is sort of a Facebook view of the project. These are our friends and partners. There are NSF hydrologic observatories that install our software, and this is our sort of testing ground where we experiment with and see what works, what doesn't work. We work with several government agencies, and again, it was great to have a talk by John from Andrews, because I'm going to talk a little bit of how we work with Andrews. Andrews has a fantastic data archive that goes back to 19th century, and we're trying to bring this data archive to life by exposing it to web services. The 3 main components of the system are: we have a publication environment where you can download software from our server, install it on your machines, and if you have hydrologic time series that are being collected at the university, you can use the software to publish this as web services. Then we have a mechanism to harvest these information, metadata, what we publish, into a central archive that becomes sort of a central one-stop shopping place. And from there, we can feed a bunch of different client applications. The main clients that we're working on now is called Hydrologic. Okay, many different types of data that we have to process. Very many sources of data. We get time series from USGS, EPA, National Climate Data Center, Department of Agriculture, not to mention states, programs, not to mention university programs, and there are hundreds and thousands of them. And the issue is that all of them generate data. These arrangements, they may have different conventions about how you name variables, how you describe them. So when we try to create a common network, it becomes quite difficult to search it because we need to establish some commonality between these networks to make some meaningful searches. So this is network of federal data overlapped over each other, but we also have state level and local level. So these small networks appear anywhere where people collect data. And if you want to search across of them, you would need to have a mechanism where at least we would know that these networks exist. And then we need to get in there and discover what is common about this network so we can search and retrieve it. The old way was an agency or a research group or university that publishes data. And that would be a website. In the best examples, this website would allow you to go through a series of forms, enter say station or select station number from a list, select parameter name from a list, and then eventually you get to an ASCII file or something like that. That will give you the values that are there. We try to make it, and the problem is that each organization will do it differently. So from USGS, National Water Information System, you will get ASCII response. From EPA, you will go through a different series of forms, and you will end up XML file. And that also is more resistant before the just format. So we try to make it all much simpler. This is sort of a common data model that it's actually simpler than this. What we have is values, and values will have some attributes. If you want to describe information about what would matter, you would need to have a timestamp, you would need to have location of the matter, you need to have, if you describe location, then you probably need to specify what sort of system it is in. If it's time, local time, UTC time, zone offset, these are all important ingredients because if you want to interpret this data several years after it was collected by somebody who has not collected this data, that person will ask these questions. So we have values, we have sites, variables, sites, and there are a bunch of hook activities, but these are extremely important. What is happened, where, and once we establish that common model, we need to have a mechanism of how we relay this common model in a standard way between publishers of the data and consumers. So we came up with a language called water markup language, which is an output XML schema for water data. This is an example, and it's in fact, well, I know that showing XML on any slide is a short way to kill any presentation. But here is actually a very simple example. We have values, there's a quantifier, A stands for approved, this is coming from USGS, there's date time, and there's a value. Very simple, something that your program can take and use it to generate a chart. Or if you have many of them, you can do something more fast. So how it works, your client application sends a request, and there's a set of standard requests. Get sites, give me all the sites that you have in mind. Get the site information, describe what patterns you have at that particular site. Give me variables that exist at the site, and values. So that request goes to distributed providers of hydrologic data, which could be USGS or could be academic data sources. And the data are returned in some format that is then converted into water ML, so that clients would only need to understand water ML. This means that adding more publishers into the system becomes fairly easy. Right? You just need to make these publishers publish water ML publishers or convert somehow what they publish into water. And that became a fairly useful model and quite convenient model, so that we have at this point about 65 publishers in the system. We have lots of requests and all of the communications go over WaterML. Now, WaterML was just our own invention at the beginning, but many agencies have the same problem. If you want to create interoperability at the global scale, you have to follow standards or engage in a standards development process with a group that has a good track record. Open Geospatial Consortium has a very good track record of that, and World Meteorological Organization as well. So jointly, these two groups formed a Hydrology Domain Working Group that is a group of researchers. We get together at least 4 times a year at different locations at OGC meetings. And the idea is to come up with a common language. It's now being referred to as WaterML 2. That would implement the most common use cases that are supplied by different agencies and provide common description feature model, observations model, common semantics, and common software stack. Software stack is common. I'm a co-chair of this group, so if you want to get involved or get more information on this website, just ask me. That's another simple picture that shows you just a general outline of the system. We have a software stack that allows you to publish the data at the university. So if you download the software stack, it includes some data conversion tools that take your Excel files, or if you have some data logger that where you stream real-time data in your system, we can capture that and load this in standard canonical representation called observation data model. On top of it, you can configure web services so that your hydrologic data become available as WaterML and hydrologic data service requests. The same thing happens with, so there are 2 types of service. Some of them are built from entirely free set of components, and others rely on SQL Server from Microsoft and RJS Server, which requires. Same thing is with external data providers. They are wrapped as WaterML providers. These data from all of them are harvested into central application. And the central application handles, maintains the metadata catalog, manages different semantics. We'll talk about different semantics later. But you can imagine that with about 15,000 parameters, or more than that, measured by USGS. Well, if you look at the list of parameter fields that USGS contains, National Water Information System, there will be about this number. There's about the same number of what EPA measures, they call it characteristics. And CDC measures yet another set of things, they call it elements. There is no one-to-one connection between what they measure. So if you want to say, I'll give you examples. But back to the system. Ontology management control for keywords, we need to establish some common ways of how we describe values and variables and mediums. So there's control list of terms that can be used to describe the medium where measurements are taken. And once we have everything available to WaterML services, different types of clients can be used. There are clients that are desktop clients, so you can call this data from Excel, you can call this data from RJS. And also there's new, very nice clients that is being in beta now called HydroDesktop. You can go to hydrodesktop.org, download it, and you will have access to the entire set of resources that you have in the system. The one-stop shop, it's HA Central catalog. We have about, as I said, about 60 services there. And if you want to register, you say you download the software, set up your server, you now have water services, we can go to this site and register the services. Then you become, then the index is activated from social features. And you can search this from an online tool or from desktop tools. So this is what we currently have. We manage 15,400, actually more variables these days. That's a very big number, and it creates a lot of additional problems. The sites come from USGS, from EPA, from NCDC, from NOAA, from Department of Agriculture, and from about 55 or so academic sources. We have 23 billion series, and it seems to be the largest water data catalog that exists, where all the values are accessible from web services. So if you write an application that will be making water and oil requests, these information will be available. This is what we have from federal agency sources, and one very important change that happened just in the recent year and a half was that agencies started to adopt our language and our way of serving this data. USGS, National Water Information System, now has a web service that returns data values in water format, and unit values these are 15 minutes interval near real-time data also come from this water format. Same as with National Climate Data Center, where the data service our integrated data systems are available as water and oil. So, in that way, we solve this sort of the structural problems. Yes, everybody has a different structure. Now we see that everybody on WaterML, and we do something to make this happen, either route this into WaterML or provide software stack that allow you to circulate the water. But there are also semantic issues. Each water data source uses its own vocabulary. Idiosyncrasies are hard to manage when we do with semantics. Just some examples, we have different measurement units. Parameter names can be referred to differently when you try to combine, when you look for nitrogen in the system. They may be misspellings, but they can be just different meanings. This is my favorite. This love oxygen. And what we have is a common ontology, a common set of terms that we encourage data publishers to use. And sometimes data publishers are hard to encourage to use any terms that are not their own. So we have a mechanism of how you associate these terms with local terms with these terms. So we can do search based on the common ontology. This common ontology looks like this. So it is actually a dynamic system where you can navigate. There are about 4,000 terms here. Of course, when we build biological data, it becomes quite manageable, but chemical and physical characteristics of water quality or quantity. These are the types of parameters that we use and stuff. So we have the interface where when you publish the data, you open this interface and associate variables that you harvest from your data. It's part of our metadata harvest. You can associate these variables with these terms. Once you do that, you can search based on the terms, and in some cases you find nitrogen, a certain type of nitrogen, as measured by USGS or as measured by EPA. Variations in the names may be different, but you can sort this out easily. Right, so this is the tagging interface. As a data manager, you publish your data set. We scrape the variables from your data set, and now you can just map variables in the data set with this process. And when you search, you you may end up with variables that come from different sources. So your search for nitrogen will result in different types of codes that come from different repositories. Of course, that was our own rendition of the ontology, and different researchers will have different ways of how you build that tree of concepts. So we have a new grant that shall start later this year that will try to organize a community process of updating this ontology. One way to do that is with so-called semantic wiki, where you may be familiar with wikis. It's an editable web page, and it's hierarchically organized. And we have a hierarchical concept here as well. So imagine that each page is equivalent to a concept, right? If you want to add a concept, you just add a page, and on that page you can describe, you can give a definition of that concept, you can describe how it relates to other concepts, you can relink pages in this representation and so on. So that would be a community way of providing feedback as to what would be the most logical way to Hydro Desktop is an application that both GIS and hydrologic analysis, so you can get time series from different sources and put them together. We have extended this to actually multiple projects. By now, we talked about USGS real-time data, so one connection was with open source data turbine that allows you to process real-time data, and we passed these 7,500 stations that are USGS real-time stations through that engine, so that you can see how gauge height and discharge vary in change stations. The same approach has been used in CUAHSI approaches have been used in several projects that sort of has been started after CUAHSI, including projects funded by NIH. This is a very large project that deals with ocean observatories. CZO stands for Critical Zone Observatory, so it attempts to integrate different types of data, including geochemical, geophysical, hydrologic, atmospheric data for selected experimental watersheds. Conservation International, I will show you an example later. Also uses CUAHSI, and we also have installations in other countries. It's actually quite important that the standards that are developed and the technology we develop is tried out in different countries. Within OGC, Open Geospatial Consortium, this has been a very important theme because the way it works is there are interoperability experiments between different countries. For example, France and Germany experiment on exchanging hydrologic information in the right level. And actually, this experiment is going on right now. They're setting up servers and using WaterML to exchange hydrologic data. The same thing happens with groundwater in the Great Lakes Basin between Canada and the US, with USGS on this side and Georgia. A brief summary. So we're trying to create cyber infrastructure for hydrology. One place must talk about for hydrologic data. Of course, it doesn't cover all aspects of it because we still are not working with publications, third party type publication hydrologic data with essential publications. But when you submit a journal paper, you have to many journals are required to submit your data set, but in what format you submit this data set, how interoperable least the rest of the data. These are all issues that are not really specified. So if these solutions follow the standard establishment, we can ensure that it will be interoperable within the system and eventually progress in the interoperable services. Yeah, it's deployed on water around this language that seems to have life on its own. It is a subject of international cooperation. The number of hits that the system has been getting by the middle of this year was about 10,000 per day for discovery queries and 3,600 per day for data downloads. And it's, I don't have it beyond May, but I know that it went up because it was worse. 60 students hit this catalog quite a bit. We have several proposals in the pipeline, and one of the ideas is to set up operational services. So the catalog and the Hydrologic servers have been successful enough so that it would make sense to maintain them beyond the life of the research project. Another extension, and this is where I really hope we can now some shared ideas and discussions with libraries, is how we can do long-term preservation and archiving of hydrologic data. Because essentially we are looking at how we preserve chemical records, and these are topics that are not foreign to you. How we provide quick search over these multiple records, how we index different types of data, how we provide visual search over these different types of data. Speaking of visual search, I think that I played this last night and I think there was some function touches on this visual search application in a project where that actually uses some CUAHSI technologies, but this is a nature conservancy project that deals with agriculture in Africa. And let's look at irrigated agriculture as opposed to you can do histograms, you can do get grid views, you can limit it to a particular level on extent or elevations. So this is a way when you have multiple documents or multiple images, and this is what libraries has. That would be a useful way to manage it. And these images can be integrated with other types of that was it. I actually, if I have more time, I could about 5 days was.
Well, thank you.